3b. Hopefully we've gone okay with 3a. Hopefully we've sort of wrapped that up a bit. But 3b today, we're increasing and decreasing functions. So we're looking at specifically using calculus techniques to find out when a function is increasing and decreasing, okay? But we can just refer to its graph. So, for example, if I have this function here, okay, let's say this is a cubic of some variety, and I'll just put a and b here. It's increasing if as x increases, y increases. So you can think of yourself walking along it, you're walking up a hill, it's increasing, okay? If you're walking between A and B, you're walking downhill, it's decreasing, and then we have increasing again. So if we were to describe this one, we would say it's increasing for x is less than A, we include the point, and for x is larger than B. All right, that's where it's increasing, and then it's decreasing between those two intervals. So that's just a bit of a recap. So let's use we can use the graph. Okay, you can look at the graph and you can see, you can G-solve those points, but let's use calculus techniques to see why that's true. So I've got here a quadratic, and our process is to differentiate it, so to find the derivative and draw its sine diagram. So here's the derivative, 2x take 4. Okay, we want to draw the sine diagram of the derivative function. So if we want to draw a sine diagram, we need to know its roots. Okay, so I'm going to go, when does it equal 0? Okay, what we'll have, we've got a root at 2. Okay, now this is the sine diagram of f dash of x. F dash of x. And I'm building up this sine diagram here. I know this line here, this is f dash of x, right? The derivative function. It's the equation of a line and it has positive slope, which means if it's a line, it's going to be going like this. Okay, which means it goes from below the x-axis to above the x-axis. If we have negative slope, it would be the opposite. We've just got to think about it in relation to the x-axis. Okay, now this is the slope function. This is the sine diagram of the slope function. This tells us when the original function has negative slope and when it has positive slope. And if it has negative slope, that means it's decreasing, you're going downhill. If it has positive slope, that means it's increasing, you're going up. So we can look at this and then make a statement about the original function. Okay, f of x is increasing. Okay, when does it have positive slope? For values larger than 2, and decreasing for values less than 2. Okay, so what I've done there is I've made a purely algebraic mathematical argument, okay? If you were to look at this graph, okay, you could look at the graph and see that that's true. If you graph this quadratic, okay, it's going to look something like this. Okay, there's the quadratic. And that has an x value of 2. And so what you can see is before that, you have negative slope, it's decreasing. After that, you have positive slope. But what we're doing is we're using the derivative function and its sine diagram in particular to inform us about this function. Let's move on to the second one where it's going to get a little bit more complex. So our first step is to find the derivative. We have one function divided by another. We're going to use the quotient rule. U is x squared take 5x plus 36. U dash will be 2x take 5. Vx plus 2, v dash will be 1. All right, we'll smash all that together. Okay, so I've got u dash v take away uv dash, and I've made sure I've put that in brackets so that this negative distributes to every term in there. And what we're going to do now is expand the top and collect like terms along there to simplify it.
The 36 is negative.
Thank you. Oh, in the question.
Mm-hmm.
All right. Disaster. There we go. Right, so I'm going to just perform this expansion just using FOIL. 2x squared plus 4x. Okay, so that's our derivative function, and I'll let you guys process it a little bit. X squared plus 4x plus 26. So we want to draw the sine diagram of the derivative function. Now, in order to do that, we need to find the roots and any asymptotes. We can see pretty clearly there's going to be an asymptote at x is minus 2. That's because when we put minus 2 into the function, we've got minus 2 plus 2, which is 0. We're dividing by 0. We can't do that, so there's an asymptote at x is minus 2. So we're going to consider then this part of the function, x squared plus 4x plus 26. We want to know when that equals 0, or even if it equals 0. Okay? So a couple of ways we could go about doing this. We could try and factorize it. We could use quadratic formula. We could use our calculator. Okay? What I'm going to do here though is I'm going to remind you guys of something we learned in year 11 as a way of checking to see if there are any values of x that make this true. Are there any solutions to this equation? Okay? If you remember from quadratic formula, it's okay, that's quadratic formula. And this part in here, does anyone remember what that part's called? We have a special name for it. Very good, discriminant. It's b squared take 4ac. Okay? And for this function to have roots, the discriminant has to be larger than or equal to 0. So b squared take 4ac has to be 0 or positive. So with this function, let's go ahead and find the discriminant for it. All right? The discriminant of this function is going to be b squared, 4 squared, take 4 times 1 times 26. We've got 16 take 104. We've got negative 88. Okay? Now the point of this is to show if we were to try and, we can't find any roots to this because we're going to have the square root of a negative number. There's no real roots. So what that means is x squared plus 4x plus 26 never equals 0. There's no values that are going to make the top equal to 0. All right, so there's no roots of this quadratic. Okay, so then I might jump over here. Okay, so now let's think about the sine diagram of the derivative function. Okay, if we're going to draw its sine diagram, we know there's no roots, but there is one point of interest, which is the asymptote at x is minus 2. So we denote an asymptote with a dotted line. And then we want to know where is it positive and where is it negative. Okay, so remember the way we do this with a sine diagram, if we're going to develop it manually, is we go, what's a number that's right of minus 2? The easiest one's going to be 0. So let's investigate f of 0. We're going to put x is 0, f dash, sorry, we're drawing the sine diagram of the derivative. We're going to put x is 0 into the derivative function. We're going to have 26 on 2 squared. Okay, anyway, the value of it's not important. What's important to us is that it's positive, okay? Because that tells us that our derivative function is positive over this interval, okay? We'll do the same for a number to the left of minus 2, all right? So minus 3, what's f dash of minus 3? This one will require a little bit more processing. We're going to have minus 3 squared. Take 5 times minus 3. Sorry, that's the original function. We'll put it in the derivative function. Alright, so don't make that mistake. Here's the derivative function. Minus 3 squared plus 4 times minus 3 plus 26 on minus 3 times minus 3 plus 2 squared. Okay, now at the bottom here, it doesn't matter what our value is. This is always going to be positive because it's squared. So we don't really need to consider the bottom. We know that the bottom is going to be positive. But I'm going to evaluate it normally anyway. I'm going to have 9, take 12 plus 26 on 1. What have we got? Minus 3, we've got 23. Okay, and again, what you can see is it's positive. All right, it's positive. Okay, so we've done all of that manually. We don't have any idea what this graph looks like. Okay, we don't have any idea what it looks like, but we have built up the sine diagram for the derivative function manually, and now we're ready to make statements about when the original function is increasing and decreasing. So I might just do that right below here. I'll go 23 here. Okay, so what we can see is it's increasing for x is less than minus 2 and x is greater than minus 2. Notice how we don't include that point because it doesn't exist when x is minus 2. So we're increasing, and decreasing is never decreasing. Decreasing never. It's always increasing. Okay. Any questions about that one? Alright, so another way we can do this one, I've used a purely algebraic and calculus process here. We can graph this function, and you would be able to observe this. Okay, you're going to see that it doesn't exist at minus 2, and you'll see that it's increasing for all other values of x. Okay, our last one is f of x equals e to the power of x. Alright, so what's our process? It's find the derivative. F dash is going to be e to the x. Alright, we want to find the roots of the derivative. So e to the x, what are the solutions for e to the x equals 0? There are no solutions, okay? It does not cross the x-axis. And what we should do, like I'll show you guys this as well. Like if we think of any number of x, it's always going to be positive. All right, so let's say if x is 10, we're going to have e to the power of 10. What does that mean? It means 2.7 times 2.7 times 2.10 times, okay? So that's a positive number. Even if we have e to the minus 10, okay, what does that mean? It means 1 divided by e to the positive. It's still a positive number, okay? So that regardless of the x value, e to the x is always positive, all right? Which means it's increasing for all values of x. X belongs to the set of all real numbers, never decreasing. Super fantastic. So let's have a go at 3B, sorry.